row 121 shows no internet connectivity. Don't worry about it. Use your phone. Um, I will send it.
No, it's working. YouTube तो खोलना.
Log into sign my here. So you can do it from there. Yeah, it's in my. You must have sent it from January, no? Yeah, yeah, I have sent. So send it. BCC में से copy करेगा. Which account you do it from? New link or I will just send it on Twitter. Just ask. No, no, it's okay. Okay, you need. This isn't working. 5% what we can try. Just get one. So take off. You have to hold it in your hand. You need. Just keep it. Unmuted. Yeah.
Hello and welcome to Chai and Why, and really sorry for the delay. We thought we would be smart and give a link yesterday, but somehow software couldn't get it to export to that particular link on YouTube. I hope you can watch it on YouTube. If you're watching it on YouTube, please do put in questions in the comment section. Similarly, Divya Shankar, are we on Facebook Live? Can you mute your computer, please? Just mute the. Okay, so this is another lockdown Chai and Why, and another Chai and Why done with basically just a webcam and whatever we could find around. So it's going to be a little experimental, and we should have been at the Ruparel College. Unfortunately, we've not been there. It's a lovely place to do experiments, but we'll have to try and do it in basically our student office over here. So today's topic is something which I hope you all managed to get, which is a candles. We're going to work with candles. And please do make sure that you have a few candles. They could be these birthday candles, they could be the standard white candles. You're also going to need at least one glass to cover the candle with at some point. And if you have a plate with water, that's good. Kids, if you're doing this experiment, be sure that there is an adult to help you. And especially since you're lighting these candles, etc., make sure to do not burn your house down. That's not what we want you to do. We want you to do very safe experiments. And just make sure you've got your stuff. You might need a little plate. It's good to keep your candle. Can you just show them the candle which has been put on a flat thing or a plate? Just show them the candle out there. Just put your candle on a flat dish or something, or you can use a plate like this. Something like this is good, and we will then get along. Okay. So people who are watching on Facebook, again, please put your questions, comments, etc. on Facebook. Now, this is actually one session which is really a thing about interaction. It's about asking questions and finding answers, and also at times I will request you to put comments on the YouTube chat or the Facebook page. So so please do that and help us along. Okay. So experiments on candles to sort of demonstrate some very basic science principles has been around for a very long time. And the sort of hero of the story way back in 1848 is somebody you've definitely heard of, Michael Faraday. And there are just two pictures that I want to show you in this thing. So let me just see if I can show you Michael Faraday. Michael Faraday gave a set of six lectures, which were called the can you hold this? Which were called the chemical history of a candle. So Faraday gave these lectures. Oops. It's called the chemical history of a candle, and I just printed the cover of it. One of us should read, not both. That's the cover. This is lectures given in 1848. Amazing. And what he said is, there is no better, there is no more open door by which you can enter the study of natural philosophy, that's what the sciences were called, than by considering the physical phenomena of a candle. So a candle can teach you a lot of physics, a lot of chemistry, a lot of science, natural philosophy, and they called it that. And Faraday made another comment in that, which I think is very relevant in today's world of COVID and responses to COVID. He says, shall we educate ourselves in what is known and then casting away all we have acquired, turn to ignorance for aid to guide us among the unknown? And clearly, this is a time where we are faced with an unknown, and we should not go by ignorance, but follow the science. Okay. So, candles have been used for. By the way, the chemical history of a candle. This thing is available in many. The PDFs and all are available online, many websites. Please do take a look at it. And there's another very nice article by Joel Walker, G-E-A-R-L, Walker, Scientific American, 1978, which is also a very, very nice description of all the fun stuff you can do with a candle.
Nice description of
So
all little fun stuff
candles.
you can do with a candle.
Candles obviously have been around. We use them all the time. We use them to celebrate. It's your birthday, you put candles on your cake. If you want to either mourn somebody, protest something, you take a candlelight vigil. So in happiness and sorrow, we all use candles. Candles are used in ceremonies and churches everywhere. They use for light. They use for keeping time.
Maybe keeping time. You should have said 11 minute के लिए candle लगाओ और science करो, right?
Well, burning candles at 9 o'clock for 9 minutes is not going to help much. That was symbolic. I forgot the symbolism and thought it would really work. That's a different story. But the first thing we can do with a candle is candles are used on birthday cakes. And so here is a candle. I have a candle with me. And what I'm going to do is, I don't know whose birthday it is today. Is anybody having a birthday of the listeners? If it's your birthday today, happy birthday. And what do you do on your birthday? Candles on your cake or something and blow out the candle. Okay. So my question is this. Happy birthday. Why do candles blow out? And by the way, there are so many people who have birthdays today, I'm sure, across the world. But I would like to sort of say happy birthday and blow out a candle for 3 people in the sciences of very, very different types. And let me again show you my happy birthday page. So here is a set of people I would like to really wish happy birthday to. And there are 3 people of 3 very different kinds of personalities. So I'm going to start with Rosalind Yallow. And this is one person you probably haven't heard of, but you should. She was a physics student. In fact, she was the first woman in her time at the University of Illinois at Urbana-Champaign as a lecturer, as a teacher among 400 men over there. And she had a really very tough struggle just because people didn't take her seriously, just because of her gender, but she persisted and she became an expert in radiology and medical physics and developed the technique of radioimmunoassay, which is very, very important in the world today. We use it for diagnostics of a lot of different kinds, and for this she shared the Nobel Prize in Medicine in 1977. So happy birthday, Rosalind Yallow. And the 2 other people whom are, of course, you've heard of Jayant Narlikar, who is an astrophysicist. And of course, apart from that, I think many of us have also not just been influenced by his lectures in astrophysics, but by his writings. Both writings on general science as well as science fiction. And he's an amazing writer. And the third person is, again, somebody you may not associate with the sciences, Brian May. Brian May is a lead guitarist of Queen. Songs like We Will Rock You, Bohemian Rhapsody, etc. But he has a PhD in astrophysics, and he was one of them, people who break for 30 years and then completed his PhD in astrophysics. And he even was part of the New Horizons Science Collaboration when the space probe went to past Pluto. And so scientists come in all kinds of, they have very, very different lives, and these are 3 people who have their birthday today. Let's see. Let's get back to our candles. So let's see, we're going to focus on this candle for now because we're going to basically do experiments. I can bring that down there, right? The easiest thing is to bring this down here. Just Okay. So the question was, why do candles go off when you blow them out? Let me get this here. There we are. Okay, that's the top view of a candle, which is. We should shift this rate of water over there. you have a slightly better view. Candle. So here is a candle, and what happens when you blow it up? So you can take a candle and blow it out. Question is, why does a candle go off when you blow it up? Okay. So if you're putting in things in the chat, please put it in the chat. I'm going to look at the chat in 30 seconds, and then. So I'm just going to check the YouTube chat, and let me see if anybody said anything on why the candles go out. Let's see. Has anybody said anything? Okay, we will try and fix the echo as well. Okay, guys. Audience, online audience. Give us 2 minutes. I'm going to try and get the echo on YouTube. Can you figure out what's causing the echo? Is anybody still on? Are you on YouTube? Nothing, right? You're not enabled. Okay. Is this mic enabled by any chance? Your mic is on.
I'm muted now.
Okay, shut your video also.
No, this is being live streamed.
And it's on Facebook.
I can't check. Can you check on Facebook? Okay, I've got it. Yeah. I don't know. Okay, that's this thing was unmuted. Okay. So now it's muted. I think there is no problem.
Okay, so is the echo gone? Can you hear us now, live audience? I'm sorry, I have to somehow keep going back to the another computer on which there is the YouTube stream to check this.
No, someone replied.
Okay, folks who are listening, Siam, etc. Somebody's thing is, I can hear it here.
Facebook पे नहीं हुई.
So don't turn on anything. Don't turn on anything. But don't check it from this room. Go somewhere else and check. Please. Okay, guys. Really sorry for this. Let's get on. Okay. So I assume that there is no echo now. Fantastic. Thank you. Please bear with us. We have some really crazy way of doing this, and so let me just say what we were trying to do. We were trying to figure out what happens. Why does a candle go off when you blow on it? So yeah, what do you think it is? So just put your comments in either the YouTube chat or the thing. I'll look at it. Okay, all good for the thank yous, but let's see, why do candles go off? How about somebody answer that? Okay, so somebody has to monitor this light.
you were just in some cases. Yeah, you got to control the camera as well. So Suryan can control camera. You can.
Okay, so many people actually, I've done this experiment many times, and often the most common answer we get is the candle goes off when you blow it. When you blow it, the candle goes off because of the carbon dioxide in our breath. And that is probably the most common answer we get, that the candle goes off because of the carbon dioxide in our breath. And that is actually not correct at all. You know, we breathe in air, which is about 20-21% oxygen, but we don't use all of it. We use hardly 4% of it. So the air we are breathing out, the exhaled air, is still 16% oxygen, and that's enough for a candle to burn. So candles don't go off because of the carbon dioxide in our breath. Well, then what could it be?
Someone answered, because when we blow on it, maybe the required amount of oxygen is no longer available.
Exactly. This is the most common answer we see, because the oxygen is not there, but that's not the answer. The answer actually depends. To do that, we need to understand how a fire is sustained. If you want to have a fire, you need three things. You need something that will burn, which is, in this case, wax in the candle. You obviously need oxygen for it to burn, but you need a third thing. And the third thing is you need a source of heat. It must be hot enough to burn. That's what is called the fire triangle. Are we frozen or something? No. Okay. So what we are doing actually when we are blowing a candle is we are reducing the heat. We are removing the heat so fast from the flame. So when I take it and blow it out, what I have done is I have cooled the region to a point below which the wax cannot burn, and hence it goes out. It's not oxygen. Okay. In fact, you can collect your breath in a balloon or something, and blow that into a flame. It will happily keep burning in that. Okay, so that was the first thing. The birthday candle blowing off. Candles go off because you remove the heat. It's not because of the carbon dioxide in your breath. All right. And of course, the next thing to do is to look at a candle flame carefully. In science, everything is about observation. And in this case, it's going to be a little difficult, and I hope you can do it with us at home, because the camera is so sensitive. It actually you can't really see the colors in a candle flame over here. So maybe if you look at a candle flame carefully, it's yellow. It's yellow, and this is very different. You must have seen another flame at home in your kitchen, the cooking gas, which is sort of mostly blue. So the next question we can ask is, why is a candle flame yellow, whereas the cooking gas flame at home is blue? Okay, so why is a candle flame yellow and a cooking gas flame at home blue? And this, again, surprisingly, is something which we've asked many times, and many people actually really give very different answers, and which is good. This is how we think. We think this may be a reason for what happens, and then we actually find out what it is. So if you look at a candle flame carefully, and it's gonna be difficult to show this on the video, but if you look at the flame carefully, you will see that the flame has a few regions. The region which is sort of in the center, it's dark, just above the wick. The region in the center is dark. Is there any way we can sort of make this still a little larger for them? Raise this, close this. Now we can bring this down because we are done with this. So we can remove these
3 books.
Yeah, we can remove 3 books. Our height of the webcam is adjusted by putting a number of physics books. That's the sort of, yeah, this is good. This is good. This is good. This is much better, much larger. Yeah, in fact, you should take a picture of how the candle is sandwiched between a Resnick and Halliday and an Ashcroft and Mermin in this side. Okay, so that's fine. That's fine. Let's just keep it there. Okay, so in the center, it's actually dark. The edges at the bottom, you may see a tinge of blue, and most of the flame is yellow, and the tips might be slightly a little darker shade of yellow. That's how a candle flame looks, and this is very different from your gas flame at home. And why is this happening? Okay, so let's see. Again, you can post something if you'd like in the chat comments. I'll quickly take a look at them and see if we can tell you what it is. Okay, so if you're wondering why the candle flame is yellow and the gas is blue, let's tell you. Let's think of why it could be. So one of the reasons you might think is, well, temperature. You know, we've heard of something called black bodies, where if you heat something, it initially becomes red hot. You make it even hotter, it becomes yellow hot. You make it even hotter, it becomes whitish, and then bluish hot. When it's if you take a piece of metal and you heat it up, it will become dull red, yellow, orange, eventually become blue. So that's what they call a black body. But this is really not so, because if one had to make a flame which was hot enough to be a black body kind of blue, that flame would have probably a temperature of 10,000 degrees or something, which is obviously not the case for a gas flame at home or even the candle flame over here. So it's all a matter of what is burning. Well, what is burning? The wax is burning, and it's combining with hydrogen, with oxygen in the air. The hydrocarbons in the wax combining with oxygen in the air, and let's see. You can see this. You can sometimes hopefully see the smoke as well from this candle. Gives you some black smoke, forming particles of carbon. Okay, and if I actually blow on this, if I blow on so I've got a little tube here with which, that's my phone. Just kill it. So if you just blow, and I'm going to carefully try and blow on the flame without putting it off. So I've got a little pipe here. Let me put this more towards the center. Let's see if I need to move it. Okay, we can move it down. Okay, so here is a pipe, and I'm going to try and gently blow. Without putting it, oops, it's gone off. Oh, we'll have to light it. We should have another box here. You can try with a straw. Maybe we should keep another candle burning so that we don't keep having to light this. Okay, I'll try with this one, so I can always. Goes off very easily. So if you blow on it and give it more air, Suryan's probably the expert in doing this. It actually, you'll see that it's slightly bluer. So this color has got something to do with how well the candle is burning, how much of oxygen you have. And it turns out that the yellow of the candle flame is just because the candle flame does not burn very well. It generates lots and lots of carbon particles. It generates a lot of soot when it's burning. And if I take a plate, can I just use, or I'll just use something. I'll use this. And I hold it on, I'm just going to take a little, I just have a little pipe, and I'm going to hold it on top of the flame, and hopefully you will see that very soon it's going to get coated with something which looks black. There it is. There, it's black. And the black, this is carbon. It's just carbon particles. And the yellow is because of the carbon particles which are getting hot and glowing. It's like when you have in Diwali, you have these fine fulzari particles which are hot and glowing. They're yellowish in color. It's the same hot soot particles which are glowing. And if you blow on the flame very carefully, you can. Oops, it went off again. you can probably see it's slightly bluish. Now, why is it bluish? Again, it's not because of the heat. Your gas flame at home is also blue because of something called, again, carbon, but not as carbon particles, but as C2. And this is, if you want to find out about this, please read about something called swan. Yeah, there it is. If you can see it with your eyes very clearly, unfortunately, it doesn't pick up on the camera very well. If you take a straw and blow near the flame just before it goes off, or even if you can blow carefully, you'll see it's mostly bluish before it goes off. Okay, and the blue is because of these what are called swan bands of carbon or carbon 2, and the gas flame is blue because you don't have these particles. You don't have the carbon particles which are incandescent and glowing yellow. The yellow out here in the candle flame just overpowers the blue totally. That's why you see this as yellow and not as blue. Okay, any comments that we need to look at? There's no feedback, so it's really crazy. I'm almost talking to a wall over here. Okay, so remember the
incomplete combustion.
so in a candle flame, the wax is not burning completely. The hydrogen and the carbon, they don't get enough oxygen to burn completely into carbon dioxide and water. So there are lots of carbon particles, and the carbon particles glowing are what gives you this yellow flame. In your gas at home, you actually, the burner design is such that you mix a lot of air into it, so it completely burns, giving you carbon dioxide and water vapor. And what you see is a blue color from these carbon 2, that's what are called the swan bands. It's not because of the temperature of the flame and the black body effect or anything of that sort. So are you telling me that you must be wondering, I'm saying that the flame is not burning fully. How do we see that? So, you notice that the center of the flame is very dark. We've said that the center of the flame is dark. What if we could cut the flame at different heights and see whether it is really burning or not? This is what, a candle flame is what this whole idea of incomplete burning, because what you have is you have wax, which is molten, it's going up, it's rising from the wick, and it meets the air. The air is coming from the outside, and they have to meet somewhere, and then the reaction happens, it's burning. So in the center, there's actually a region where there's just hot wax that's not burning at all. But how do we cut the flame and see it? So let's try and cut the flame. Okay, and now if you have this is where we're needing the top view, you might have to hold the camera. So what we're going to try and do is, okay, that's not what we're trying to do. We'll try and straighten this wick. Okay, can we turn the AC off? We have a draft somewhere. Okay, so now hopefully you're seeing the flame from the top. No, the flame is not. No, that's getting worse. Okay, yeah, and I have a strainer with me, and this is a metal strainer. Please do not do this with a plastic strainer. Okay, and what you can do is you can slowly put the metal strainer on top of the flame. Okay, and here it is. I have cut the flame. There it is, halfway. And can you see that the flame is hollow? I'm holding it about halfway, just above the wick. And hopefully you should be able to see that there is a region in the center where there is no flame at all. It's actually hollow, and the flame is at the outside. So the region in the center is where there's hot wax, but there's not enough oxygen that is able to diffuse through and come there and actually allow the fire to burn. So the flame is actually hollow, and you can cut this at different heights. You can move this up and down and see where that hollow is. You can move it up and down. Okay. Please do this only with a metal strainer and not with a plastic strainer. And I hope you could also see the smoke. If you're doing this at home, maybe you can see it on the camera as well, the black smoke that you get from the, you can see the black smoke on the white background. That's the carbon being produced. And actually, if I cut it here, there is even hot wax escaping above the thing. And if I could light it, there is a very beautiful experiment in Faraday's thing where he actually is able to light the wax. Can you see the flame is much, oh wait, it's your camera is not showing it. Look there. So this, which is burning here, was the wax above the thing. So now that is a drop of wax from this actually.
But so let me not use a candle. Let me use a match. I'm going to use a matchstick. Okay, so this won't drip, and I'm going to see if I can actually light the wax above this. Yep, you can. It's tough to see, but you can see it. You can see it. Little difficult. It's getting too hot for me, but you could probably
leave the match in the.
Leave the match.
Yeah.
Okay. No, it's going to go off. Oh, that's hot. Yeah, this stuff which is burning on top are the wax vapors which we have cut, and the wax vapors are burning. It's not only the match that is burning. Of course, most of it is probably also the match. But if you're very careful, you can actually see that there's white wax vapor coming out when I cut the candle in half and sort of cut the flame in half, not the candle, and allow the wax vapors to come on top. Otherwise, you see this way. So the flame is hollow. This experiment just shows that the flame is hollow. All right. So yeah. Okay. Now there was all this unburnt flame, unburnt wax. Can we do some fun stuff with unburnt wax? Yeah. Should we? Okay. Let's see. If there is unburnt wax, I should be able to light it. So this is what is called the jumping flames demonstration. And so I'm ready with another candle. And okay, what we just zoom out a bit. Good. Okay, we're going to blow this candle off. And you see there's white smoke. And I'm not going to touch the wick. I'm going to light the white smoke. Let's do this one more time. And you'll hopefully see that the flame sort of jumps back to the wick. So here we go. There's white smoke, and I lit the smoke. Now there's a little wind draft over here. If the smoke goes vertically up, you can light it even a few inches away. Let's try again. There's white smoke, and I light the white smoke. Do try this. This is fun. There we go. So the flame sort of jumps back because that is the hot wax. So there was inflammable wax vapors which were coming up. One more time. Oh, not enough. And there we go. So if you have a place which you can make it really no air in it, the wax vapors can rise. You can even do this from a pretty good distance above the candle. Let me try one more time if you can do it. Oh. There we go, and there. So this is about at least 2 inches away. It's not straight. No, this one didn't work. Okay, so that is the jumping flames, and the jumping flame happens because of the wax vapors that are actually getting lit. Okay, I think we can switch the AC on. It's hot enough in Mumbai, and in a sealed room with a couple of candles burning, it's even warmer. Okay, I think we've lit enough of candles, and now I think it's time to put them off. And the classic way people put candles off, when at least in schools, the classic experiment which is done. This candle has got too much of stuff around it, so let me try with this one. Right. Okay, so I'm going to just clean this. I'm just cleaning the droplets of wax around the place, because otherwise my glass will not sit over it. So then for the next thing, we're going to require a glass, which we will put on top of the candle and see what happens. Come on. Okay, and let's turn this guy off. Oh. Okay, so now we have this candle on which we are going to experiment. Lots of wax vapors. Okay, so let me ask you. Yeah, maybe we should do it in the saucer. That's probably a good idea. We should clean the saucer first. But let me ask them anyway. What do you think is going to happen if I take a glass like this and I put it over the candle? So what do you think is going to happen? And the most common answer I hear when I go to schools or something like this is, well, if I put a glass on top of the candle is going to go off. Really? Let me try this. I'm going to take this glass and put it on top of the candle. The candle didn't go off. Hey, let's do this again. I'm taking a glass, I'm putting it over the candle, and the candle didn't go off. Well, in science, one has to be very careful. You have to say, okay, what happens if I put a glass over the candle and leave it there for some time? But even before we leave it there, I want you to observe something. If you have a glass at home, okay, I want you to observe this at home, and I want you to see, I hope you have a glass. Look at this glass. This is a clear glass, right? You can even see the flame of the candle through it. Okay, this is clear. Now I want you to see whether the glass remains clear. Just put it over your candle, and in the first few seconds, let's see how the glass looks. Does it remain clear or not? So here we go. We've put it there. And I'm going to remove it. And if you see, you can put your finger inside, and you see it's not clear. Look how the flame looks diffused through it. And if you put your finger, it'll look wet. It'll be wet inside. It's wet. Suren uncle, did you dry these glasses well?
Yeah, they were dry.
They were dry? Okay.
You did some magic.
Did I do some magic? No, let me see. Let's use another glass. Okay, look at this. This glass is clear. Right? Absolutely clear. No problem. I'm going to keep it on top of the candle for a while and take it out. And look, it's not clear now. In fact, yes, this one's also wet inside. There's a little moisture inside. This looks almost like you take something out of the fridge and water vapor condenses around it. So somehow water vapor has condensed not outside my glass, as you would if you put cold water in the fridge, from the fridge, cold water inside a glass, but water vapor has condensed inside the glass. Where did the water come from? Well, the water actually came from the flame, from the fire. The candle flame, what is happening? The candle, the wax, it's a hydrocarbon. It's got something which has hydrogen and carbon. It's combining with the oxygen in the air and forming carbon dioxide and water vapor. Water vapor is a product of burning. And that water vapor, you normally don't see it, but if I keep something cold for a while, you will see the condensation happening on the insides of the glass. And this happens way before. Now we haven't even looked there's a lot of water in this one. We haven't even turned we haven't even put off the candle. Okay, so something we've seen, the first thing you can see, of course, the glass is warm, is that there is water coming out the candle. Now let's see if the candle actually goes off when I keep it here, or maybe you think I should do it on this one. Yeah, you can also do it. You can also do a variant where you keep the candle in a little thing. We'll put that later, and we will cover it with a glass, and let's see what happens. Again, the flame is going slowly down, and it went off. Okay, and you lift it. You see there is a lot of water. There's a lot of water inside the glass. You can put your finger and see that it is wet inside. Okay, so it worked. Let's never believe an experiment done only once. Let us see if this happens on this one as well. I'm going to keep it here, and the flame becomes smaller and smaller and eventually goes off. And if you look at your glass, there's a lot of water on it. I mean, there's water inside. Water's inside. So why did the flame go off? And this, I think, is an experiment which is probably, I don't know if it is done in most schools, but at least every 6th or 7th standard book will talk about it. Why does the candle go off when when it's covered by a glass? We'll do the water in the next part. And the most common answer, let's see, hey, why don't we give 30 seconds to people and see if they write something, and this gives me a chance to check if there are questions coming in. Doesn't seem to be anything new on Facebook. Due to lack of oxygen. Excellent. This is the answer that is most commonly given to us by students, by teachers, that the fact that you when I put a glass over a candle, it goes off because of a lack of oxygen. A lack of oxygen meaning the candle has used up all the oxygen inside. Now, let's question this thing. How do we know that it used up all the oxygen inside? Unfortunately, I can't do the same experiment that used to be done, more than 100 years ago, where the rules and ethics and things like that were different. In those days, they had a big bell jar, they put a candle in it, and they put a little mouse in it, and the candle would go off, and the mouse would still be happily running around. So the oxygen, didn't get over. And I claim that the oxygen has not gotten over, but I can't put a mouse; it won't be allowed. So I'm going to do a slight variation on this experiment. And to do the variation on this experiment, what I have are two candles. I have two candles, one which is tall and one which is short. There is a tall candle and a short candle. And we will repeat this experiment. So we're going to light a tall candle and a short candle. Before we do it, we'll explain the experiment, and we are going to put a glass on top of it. So there are two candles, a tall and a short one. Should we cut its wick off? That's okay. All right. So question is, let's do first the thought experiment. When I have a tall candle and a tall candle and a short candle, and I light both of them, and I put the glass over it, what do you think will happen? Will both candles go off at the same time? Will the tall candle get extinguished first, or will the short candle get extinguished first? So you have three choices, right? Both go off at the same time. Tall one goes off first, short one goes off first. Okay, so think about this. And while we think about this, let's do the experiment. So we light these candles. I can just light it. Okay, I can light it. So I have a tall candle and a short candle. Okay, I hope you can see both of them on the screen. Push it towards the center. Yeah, it's on the center. And I take my glass and cover them. And which one went off first? See, the smaller one is still burning. Okay, let's get this off as well. Oops. Okay, never believe an experiment done only once. So let's repeat the experiment. I have a tall candle and a short candle. I cover it with a glass, and the tall candle goes off first. So now remember that the short candle, of course, after some time went off. And oh, look at this. Can you see some white smoke? It's not enough light, I guess, over here. Oh, I put the wrong one. Okay, so tall and short. If I put this, tall goes off first, short is still burning. Okay, and by the way, you can see a lot of soot in the glass. There's black. I don't know why there's not enough light today over here. Yesterday there's not enough light here. I guess it's trying to focus. Yeah, you can see the black soot at the bottom of the glass. Okay, so why did the tall candle go off first? And clearly when the tall candle went off, the short candle still had enough oxygen to burn. So the first candle did not use up all the oxygen. And yeah, so let's think about this. Why could this happen? Why would the tall one go off first? If oxygen was getting over, then both candles should have gone off. So clearly when the first one went off, the tall one went off, there is still a little bit of oxygen left, which allows the second candle to burn. And the second candle will burn for a good bit of time before it goes off. Let's see how long. You can time this if you like. I'm going to put this here. This one went off. This one burns for a while and then goes off after a while. Yeah, there's some answers coming in. Let's see. More water vapor is cooling it. Okay, that could be one reason. Let's check Facebook if anybody said anything. wax paper was, I think, earlier comment. Okay. Well, remember that a candle, when it burns, remember what is it producing? It's producing, yes, water vapor is one, as well as carbon dioxide. And what happens is, now carbon dioxide normally is heavier than air and collects at the bottom. But remember, the carbon dioxide is heavier than air if the air and the carbon dioxide are at the same temperature. The whatever the exhaust of the candle is, whatever the thing, that's hot carbon dioxide, so it's actually lighter than air. So eventually what happens, the carbon dioxide which is rising up accumulates at the top, and that is what extinguishes the candle. And in this case, in the first case, the candle will get extinguished when the carbon dioxide at the top sort of starts accumulating. When you have a smaller candle at the bottom, that's actually generating more carbon dioxide, and the smaller candle is what extinguishes the taller candle on top. That's essentially what happens. It's not because the oxygen getting over. Now, let me actually show you a much more dramatic version of the same thing, saying that the oxygen, the problem why this oxygen, people believe that it is oxygen, is because of this very tantalizing, you have about 20% oxygen in the air. So what happens is, if I light a candle, and this is probably another demonstration done in most schools, where what we have done is we've lit a candle in a which is on a plate, and there's water over here. Okay, and I'm going to bring a glass and cover it and see what happens. So I'm going to put the glass on it. Oops. And the candle goes off and the water rises. Now, I don't know if you can see this. Maybe we can just move it to show them that it is about. Yeah, you can see that the level of the water is, no, it's not good. The level of the water is approximately here. So the water has risen about 20% of the way in up the glass, and this typically is 20% of the way. And because of this, people sort of think that, oh yeah, 20% of the air was oxygen, hence the water went up by 20%. Okay, I am my usual goofy self. I've spilled some water, so I'll just wipe it off and get on with it. Okay, that was not the easiest thing to see. Maybe we should add some color to the water. So at home, you can of course see the water, but just to make it easier to see on video, what we'll do is we'll just add a little bit of color to the water so you can see it easier. So we'll just add some color, and we will do this experiment with a dish of colored water. Okay, now can we just clean this one out as well? Is that warm enough, or are you going to heat it? It's ready. Okay. Wait, these are still not. We need to get it. Okay, that's better. Okay, so what we've done is we have stuck little candles on little, just so that we could prepare for it. So I don't know if you have these birthday candles at home or whatever. If you can do this, it's fun. What you can do is take a bunch of candles, and we've kept 3 candles in one place. Out here there are 3 candles. Out here there are 2 candles, and out here there's 1 candle. Okay. So what we're going to do is we're going to take these candles, obviously light them, and cover them with glasses. Now, yeah, I think we should start that. So
keep it on.
What do you think is going to happen? So we have candles, and these are all of them are sort of brand new birthday candles. We haven't lit any of them. You can see the wicks are still white. We're going to light these candles and cover them progressively with glasses. Now, if oxygen was only what was it, 20% or something, then, and the oxygen was getting over, then the water should rise only 20% of the way in all the cases. Is that going to be what happens? Let's do the experiment and find out. It's the best thing to do. So let us see. Okay, shall we light the experiments? So you want to guess what's going to happen? Is it going to be the same, or maybe I have another one? I can start from this. You've already done it.
One after it.
Okay. All right. So now we have one candle that is lit, and we are going to quickly cover it with a glass of water. Not with a glass of water, with a glass. We cover it with a glass, and let's see what happens. Candle goes off, and the water rises. Does this make it easier to see, or not really?
Yeah, it's
Okay.
do all the three and
We'll
then
show you all the three at the end. So next, what we're going to do is light two candles. Two candles, 1 and 2. Okay. And yep, let's cover two candles with a glass of water. Ooh, it went up, and there is, yeah, the water has gone up. It's gone up. And now we'll do three candles. 1, 2, and 3. Okay. And let's cover three candles with a glass. Okay, now let's try and see this a little closer. So let me just see if I can bring this. I don't burn my hand. We can show you. Okay, here is the single candle. Here is two candles. I can now we can take it back, so we can get both of them in the view maybe. And clearly there is more water in the two candles. And here is three candles where there is probably slightly more, almost the same with slightly more. It depends on how you do it. Now here you see this is one candle, two candles, three candles. If we were using up the oxygen, then it should have been the same. The fact that you have more water going in. Okay, this is a good angle. We can see all of them. So the lighting is also much nicer. Yeah, just keep them on top. Okay, there we go. So you can see one candle, two candle, three candle. There is clearly more water rise in the 2 and the 3 compared to the 1. How did that use, what happened? How did does that make sense? Does that really make sense? That doesn't seem to make sense at all. How come we have a different amount of water? Oh, Surya Uncle is trying to do something over here. Wait.
I'm trying to do
He's
something.
trying to do something. He's always
without
trying to do
any
something.
candles.
Wait, he's going to put a glass without any candles.
Yes, absolutely.
Hey, wait. This doesn't make sense. He's going to put a glass without any candles, but we don't have glasses.
I'm going to use a round bottom glass because we run out of glasses.
Okay, get a beaker from the lab or something.
It's okay, you know, I've already got a round bottom flask.
He's got a round bottom
you
flask.
can see this.
Which has no candles in it. I'm just going to move this out of the way. No, it's okay. It's okay.
You can see the dramatic rise of
Whoa. What's happening? Oh my God. He has no candles in it. He has Oh, wait.
No, it's still rising.
It's still rising. Okay. All right. Now we must really think about what happened. Clearly, we don't do magic. We're doing science. But let's try and get this. Let's try and line them up if we can. So that we just move them to the side a little bit so we can see them. Yeah. So this was one candle, two candles. This had no candles. He just put an upside down flask in this, and this is of course the three candles. Okay. So yeah, what's the story? Let's see if there are any comments that are coming in. Okay, so let's see what happened. So basically, this water rising has nothing to do with oxygen being consumed. As you can see, we had a glass which had or something which had no candles at all, and we got the water to rise almost, I would say, 80% of the way. So what's going on now? What is happening? And maybe we should just repeat this experiment once. Somebody seems to be on the right track, asking what's the flask without any candles hot. That's absolutely correct. So what is happening, and let's repeat this experiment. Let's repeat at least the candles experiment once. Is I'll show you how for the same candle, you can get a lot more water rising up compared to doing it again. So what we'll do is we had one more of the, we had this one. Okay. So here you saw this was one candle and about this 20% magic number. And this 20% has confused so many people because they see 20%, and think, oh, this must be oxygen. So I will light a one candle again. Is there enough water? Enough water. Okay, but we need another glass. Okay, we'll take out the 3 candle glass, right?
No, you can use it.
Okay, because I want to just compare this.
You want to compare this and compare it with the 3 team.
No, it's okay.
Compare
Remove
with
the
the
3. Remove the 3.
Also, you will get more water in the bath.
Okay. So the idea is it's got nothing to do with oxygen. The whole thing is when I keep a glass on top, what I am doing is I am trapping warm air.
Actually, light both the things.
Okay, just light one. We'll just compare one, and so this is the same one candle which I had before, and all I'm going to do is trap hot air. Now, if I keep it here, I'm going to trap a lot of hot air. I'm going to allow hot air to the air inside to become warm. Remember, hot air has a lower density. You can see, by the way, the flame has become a little unclear because of the condensation on the glass. There's a lot of water condensing on the glass. Okay, I'm going to hold it here just so that I trap warm air over here. If I trap warm air and then I put it down here, once the candle goes, this is why experiments don't work so often. It's about the same actually. It's about the same. About the same. Okay. It's what? Try again. Sure, try again.
Put it in an angle.
Okay. So the idea is if I put it very quickly, if I have now this glass is not fresh. It's also you should just wipe it. Just wipe it. If you cover it very quickly, you will not get this 20% rise also, because you will, of course, the candle is burning, you will trap some hot air. But if you keep it for a long time, you trap more hot air. If you have 2 candles, you trap more hot air. If you have 3 candles, you trap a lot more hot air. And once the candle goes off and the air starts cooling, the density of cold air is of course much more, so it occupies smaller volume. There's a pressure difference, and because of the pressure difference, the outside pressure is more, and the water is getting pushed in. So if I really cover it very quickly, you will probably get some rise. Yeah, it's about there, but it's less. That's because I didn't trap so much of hot air. Whereas in the 3 candle case, let's light the 3 candles again and see if we can really trap some hot air.
It's too far for you. Be careful.
Okay, we have 3 candles, and if I sort of, let's just wipe this again so that we don't.
Outside is good.
Okay, so now remember what happens when I'm trapping a lot of hot air over here, and I put it in, and once it cools down, it's actually going to cool in a lot more water compared to it really didn't do much this time. Okay, these are experiments which you just have to try a few times and try it out. Now, what happened in this case, the one which we had no water? What we had done is we had actually just heated the flask. when we had heated the flask and we put really hot, we had heated it by just putting it in boiling water. So the air inside was almost at 100 C or something. So we had heated it, and when we put it here and the air cooled, of course, it occupies a much smaller volume, so the pressure reduces, and then it pulled in the water. And you see, even without any candles being there, the water can rise. So the water rise is actually not to do with oxygen; it's just to do with hot air being trapped. Once the hot air cools down, the water will rise. And typically, when you do it, you will find that 3 candles gives you a. You also have to wait for it to cool down. And
No, also the
yeah. So, but that's the thing. So please do try these experiments. We will leave you with one. Let's just try this here. We will do an experiment which sometimes works, sometimes doesn't work. I have a tube with me. Now you're saying, okay, we've which one are we doing it on? That one. Okay, so let me get this out. Let's get this going. So here is a candle, okay, and I have a tube. This is a hollow tube. As you can see, this is hollow. Now earlier we were covering it with a glass, which is sealed. Now this is just a hollow tube. If I place a hollow tube on top of this, what do you think will happen? Ha! That went off. That went off. But look at it, it's hollow. I mean, I can keep my finger in this. It's a completely hollow tube. So this entire thing about oxygen, I mean, this guy could have got oxygen from the top, right? But it didn't. Shall we try this? So just once again, remember this is a hollow tube.
put a candle from it through it.
I can drop a candle through it. Okay, this is a hollow tube, hollow at both ends. So it's open to the air. It's open to the air. Okay. Now let's see what happens. What am I supposed to do? I'm going to keep this over here. Let's just see what happens once more. Okay. One more time. I'm going to keep it. Look at the size of the flame. I'm going to keep it here. It's open at the top. Remember, it's open at the top. And it goes, oh, it turned on again. Maybe it's now that gives you a secret about what's happening as well. It turned on again. And I'm not covering at the top or something. You can zoom out and show them that it's open at the top. Okay, we'll do this one more time. Let's just no, I think you have to take it out, take it back or whatever. Okay, there we go. So remember, this is open at the top, and look at the size of the flame. And if it's clean around here and it seals well. Okay, there I put it. And the flame becomes smaller and goes out. And remember, this is open at the top. What the hell is going on? What's going on here? This is freaky, isn't it? I mean, there's no reason. I mean, this oxygen whole thing. I mean, there's air can come in from the top. Why is it not doing it? All right, let's. Okay, let's do it once more. Now let me do it again. Well, now it's quite happy to burn. It can't be seen. Can't be seen. Can't be seen. Okay, but it went off because you blocked it.
No.
You put wax and blocked it. Okay.
No. I allowed the
Okay.
carbon dioxide to.
So what happened was this tube actually this
Maybe you can relate to it somewhere.
can you I mean the problem, I don't know if this is a generation that's seen a hurricane lamp. So what this tube is a long tube, hollow. The reason it actually burns in one of, so it depends on how I keep this, because the tube has got, if you look at it on one side, there is a little hole over here. there are holes.
So they blackened.
Okay, you can see
Blackened
that
it for the purpose.
the other one out here has this little black thing where we allowed the candle smoke to go in. Okay, so there is a hole here and a hole here on one side. Now, obviously, if I light the candle, let me light the candle and keep it with the side of the holes. These holes are at the bottom. Then the candle is not going to go off very easily because these holes, so hot air rises, the hot air rises and it can come out of the top. But because of these holes, cold air can come from the sides and it sort of keeps feeding fresh air into the candle. Right? This feeds fresh air into the candle, so the candle keeps burning. On the other hand, if I put it, now this end has no holes. If I keep the no holes end over here, eventually the candle flame goes small, becomes small and goes out. You can see a very nice stream of smoke. So this goes out because the candle is sort of generating carbon dioxide and water vapor. It cools down and then that thing settles down and sort of the candle smothers itself out. Even though it is open to the air, not enough air can come in. Remember, it's a diffusion limited flame. So you need enough air to come in from the sides. However, if I make these little holes at the bottom, then the air can come in because as the hot air escapes, cold air passes from the side. And what we could do is we use the same thing to put off this flame as well. So we will do that experiment again of lighting it. Okay, and now this would have burned happily, but what you can do is you can take another candle, do it from the other side, it's easier, and in this hole, instead of fresh air going through, if I supply sort of carbon dioxide from another candle, not yet. Okay, so see, Ash, but if I now it's going to burn, but if we bring in a candle and force sort of not so fresh air through it, most likely the candle is going to go off. So we use one candle to extinguish another candle. Okay, so this is a little bit of a fun trick where you give it to the audience one way and you use it the other way and things like this. That's what we would have done if it were live. Still, we hope you could follow some of these experiments at home. I know you don't have this tube to play with, but this is the same principle used in any chimney. Like in the good old days, we used to have hurricane lamps, which had a glass enclosure, which had little holes at the bottom through which air could come, and there was enough air for ventilation, and the candle could continue to be lit, but it was protected from the wind. Okay, so those were the experiments, and I'm sure you have a lot of questions. So we are happy to take questions at this point. If you'd like us to repeat any of these experiments, we could probably repeat something as well. So do let me know if you have questions and we'll monitor. Let me just take my.
If the holes should be moved up and down.
It has to be below the flame level.
Okay, so what is the question?
Now you can take it.
If the holes would be moved up and down.
If the holes were moved up and down
On the
what would happen? Clearly, if the holes were moved up and down, you have to play with it. The idea is the hole has to be below the flame height so that you can supply air to the flame. If the hole is above the flame height, it doesn't matter. You will eventually suffocate the flame. The products of combustion will suffocate the flame. In one case, of course, see, we have a tube which has the holes are on one end of the tube. So obviously, if you keep it down here, and the candle is about this much, the holes are below the candle. If you keep it this way, the holes are too far up, and no air from that will help you if the candle is at the bottom over here. That's for this part. Any other questions on all the experiments we've done this afternoon?
Flask experiment on the tray.
The flask experiment on the tray. So what we had done, where is the flask? It's gone back, I guess. The flask experiment on the tray, what we had done is essentially taken a little flask like this, kept this in hot water, boiling water, right, for a long time. So, this was in boiling water. and then we threw out the boiling water from this. So essentially you had now hot, very hot air trapped inside this. Okay, you have steam, hot air, whatever it was trapped inside this. Mostly it is actually very hot water vapor. And now once I put this in water, as this thing cools down, the air cools down, that itself will shrink in volume, but much more important, since there was hot water vapor, the water vapor condenses, and that's a very large volume change, and hence the pressure inside is lower, atmospheric pressure is higher, so that pushes the water from the tray that we had, it pushes the water inside and the water rises. That's what was happening here. And when you when you use a glass on a candle, if I cover a candle with this, it's the same thing. Initially, I have a candle. When I'm keeping the glass on top of the candle, there's hot air that is trapped. Once the air cools down, the density of for the same amount of air, warm air would take a lower density, so it occupies a larger volume compared to colder air. So once the air cools down, it occupies lesser volume. So pressure inside goes down, water from the outside goes up. Okay. Any other questions coming in? Facebook, can you check the Facebook stream as well?
Why do you say that the smaller candle generates more carbon dioxide than the taller one?
No, the smaller candle does not generate more carbon dioxide than the smaller one. When you have a short and the tall, when I have a short candle and a tall candle and it is covered by the glass, okay, so the short candle's carbon dioxide is also rising, and remember it's stuck here. So the short candle's carbon dioxide is helping to put off this one. These are identical candles, and if they are burning at the same rate, they're approximately generating the same amount of carbon dioxide and water vapor. It's not that this is generating more carbon dioxide. It's just that this guy gets, if you had only one candle, its own carbon dioxide would eventually extinguish it. In this case, it's extinguished by its own plus the carbon dioxide contribution from the lower candle.
In the last experiment, how the diameter of the hollow tube influences the time?
Very good question. That's a very good question. How does the diameter of the tube influence the thing? Now, ideally, for example, if I did this with a birthday candle, it may not work. We can even try it. Let's just take one of these. Just put the candle on. So clearly, if I had a very big, just imagine the limits. If I had a very big tube and a small candle, there would be enough convection currents inside the tube itself that would allow cold air to fall down from the sides. And if you notice, I did this experiment. Let's bring this back up. Which one?
The tube is broken.
Yeah, this is on the other end. Use that. Let's bring this. Okay. So remember, I did the experiment intentionally with a fat candle. This one, I did it with the thicker candle, one of these types. If I do to the birthday candle, let's see what happens. You see, the flame is going smaller, but it's still surviving. It sometimes works. Let's hope it works. Let's hope it works. Let's hope it works. Let's hope it works. No, it's lighting up again. It's lighting up again. It's not that easy. On the other hand, if I try with a slightly thicker candle, okay, now this candle has become very small, so I don't know if it will work or not. If I do to the thicker candle, and right now there's also too much base
Debris around.
Yeah, and it's also below the. It's very. There's so much wax at the bottom. I think there's a gap between the tube and the thing, so it's not going to seal well on this one. But yeah, for a birthday candle, the birthday candle is much thinner than the tube, so you can actually set up convection currents within the tube itself, which will not allow it to go off. So if the tube is sufficiently fat, within the tube you can have little convection currents that will keep bringing in cold air and supplying it with fresh air. So it works actually for a nice, a fatter candle. Unfortunately, if you see our plate with this candle,
There's a lot of debris.
show people the plate. There is a lot of wax which is melted on the sides. So actually, the tube is not sitting properly anymore, and even a small bit of dust, the tube will not sort of seal on that surface. There'll be some air that goes from the bottom. That always happens.
Okay, any other questions?
What is the difference in the height of the water in the 3 and 2 candles?
The difference in the water rising in the 3 candle and the 2 candle case.
What will happen if candles be this number?
Well, why don't you do the experiment? You can try 4 candles, 5 candles, you know, you get a box of birthday candles, which has, I think, 15 candles in it,
20.
or 20 candles in it. You can do a whole bunch of experiments. So, well, I mean, just try it. We've done 3, 4. Beyond a point, it gets very, very difficult to sort of catch it, you know, put it on, have enough within your volume of your glass. But you can try it. The more hot air you trap, the more water will rise. So that's typically what happens.
So is it the exhaustion of O2 or the carbon dioxide blanket that puts the flame out when you put a glass on?
Smothering.
It's both. I mean, you are reducing the oxygen certainly, but it's not a complete depletion of oxygen that turns the candle off. It's mostly being smothered by its own exhaust products of carbon dioxide and water vapor.
Why are convection currents within the tube preferred over those from outside?
It's not a question of preferred or not. It's not preferred. The only thing is, if your tube is much wider than your candle, so this will work for a thick candle and a sort of tube which is not much wider than that. It's much easier to set up convection currents, and if you have convection currents, they will bring in cold air from the sides. So that's what happens. If the convection is minimized, the chances of the candle going off before the fresh air can come is much higher. And you saw for a very thin candle, it sort of didn't happen. It sometimes happens. It's a matter of luck. You have to, you know, we've not really done experiments with a different diameter. We just took a standard pipe that was available and cut it and did it.
Does the shape of the candle make any difference in the water height?
Does the shape of the candle? Probably doesn't. You can have triangular, circular, whatever. What will matter is, of course, the amount of heat that the candle produces. Obviously, if you have a candle with a fat wick, which has a larger flame compared to a small candle with a tiny wick, you will generate more heat and hence trap more hot air and hence change the amount of water that rises in the glass.
What purpose do wicks serve in candles?
Very nice questions. What purpose do wicks serve in candles? Now, if you just had a block of wax, you could not burn it controllably. The beautiful thing about a wick, which is essentially cotton thread, which is twisted, it through capillary action, once the wax is molten, the wax is being burned, it sort of supplies liquid wax to the flame at an almost constant rate. And which is why the first application of candles, and which is why candles are used in all these church ceremonies, etc., is because candles were timekeepers. A candle burns almost at a constant rate. If there's no wind and things like this, it will burn almost at a constant rate. So the first clocks were you could have a candle and you stuck nails in it at regular intervals, kept a metal sheet at the bottom, and as it burned, the nail would fall and tong, you will get a sound, and after some time, tong, you will get another sound. You could make a little clock that way. So not very efficient, but well, you can see that it takes approximately a constant time. So this allows controlled burning. And the wax, of course, at the end of it, the wick is also getting burnt a little bit, but it's mostly just supplying the liquid wax for burning. That's the purpose of the wick. You can, of course, play with a thick wick, a thin wick, and see what happens. But if you had no wick at all, it's like lighting a block of wax. Yes, you could do it, but it would not be a controllable thing. You'll have to make a puddle of liquid, and when it burns, the whole block of wax would suddenly melt and maybe burn. Any other last questions? It's almost 12:20.
How much hot air can you trap in a glass?
Is there a limit? How much hot air can you trap? Well, a lot of it is not also hot air. I mean, the water vapor plays a very important role because see, any gas at let's just say there's a 100-degree difference in temperature. Okay, a gas cooling by 100 degrees will generate some change in volume, right? V1 by T1, V2 by T2. You can work these things out. On the other hand, if you have a vapor which condenses into a liquid, then the change in volume is much larger. It could be a factor of 100 very easily, or many hundred. For liquid nitrogen, for example, a liter of liquid nitrogen is almost 700 liters of gas. Similarly for water, a 1 milliliter of water would be a lot of steam. I don't know the exact number. So water vapor, when it condenses, will actually give you a very large volume change, and that's what really helps it in going up, which is what you saw in the experiment with the flask, where we just put a hot flask with hot water vapor in it. Okay, so let's call it a day. I hope you enjoyed some of these experiments, and do try them out at home. Candles are great fun to play with, and join us again after 2 weeks. As long as the lockdown continues, we will try bringing you some simple experiments to join and do along with us, and hopefully have some fun enjoying science. Thank you very much. Stay safe. And if you're going outside, please wear a mask. It's very important. Thank you.
If you switch off this